So we started with the implementation of Boolean expression or the basic gates with the use of universal gates. So we know there are two universal gates. Those are NAND gate and the NOR gate. Okay. So we started how to implement the basic gates with the use of NOR gate, and we also started we took one example to implement the to find out how to implement the Boolean expression. Okay, so we'll continue with that. We will continue here. So here, you know how to design, how to utilize the NOR function, NOR gate for the implementation of the basic gates. Okay, we started with that, and we have seen how to design different the NOT or and gate we have designed. Next is the NAND gate. We'll see how NAND gate is utilized for the implementation of the basic gates, and then we will use both a NAND gate and NOR gate individually to implement the other Boolean function and other gates. Okay, so okay, here what we in the NOT gate, what a NAND gate is the NOT of AND. We know that. Okay. So if we use after the AND, if we put a NOT, then that will implement the NAND gate. Okay. So NOT of AND is the NAND operation. Jessie, are you here?
Yes, ma'am.
Do one thing, you create one link and just share with everyone. Okay, the open link, so that the students are coming in between the class and I have to provide them the permission, so it is very disturbing. So you just create one universal link and share with everyone, so that I don't have to permit them. Create one a single link. Okay, and share it with the this classroom. You just upload there.
Okay, ma'am.
Okay.
Okay, ma'am.
Okay, so here we know that if the AND gate, if the AND NOT gate is used after the AND gate, that will be the NAND gate. Okay, that is the NAND operation. So one more thing is that after applying the De Morgan's theorem, we see here according to the De Morgan's theorem, what happens? A B the whole bar. This will make the NAND. Okay, so if it will make A bar plus B bar. So just the way we have done in the NOR operation, the bubbling of the variables. Okay, so this plus indicates that it is the OR operation. Okay, so OR operation with the complemented variable will make the NAND operation. Okay, OR operation with the complemented variable will create the NAND operation. Okay, so if somehow we are able to make the complement of the variable and then add, then it will be inputted with the OR gate, then it will be the NAND operation, we can say. Okay, so this is this diagram shows such kind of arrangement. Like this is the a bar. So if we pass this a with the with the NOT gate, it will make a bar. If we pass this b with the NOT gate, it will create b bar. And here the plus indicates that this is a ORing operation. So if we replace this NOT gate with the bubble, then what will happen? It will create a bubbled OR gate. Okay, if we replace this, it is possible that the bubble indicates that the NOR operation. Okay, so if we replace this inverter with the bubble at the input side, that will create the bubble. Okay, so this NAND gate is the equivalent to the bubbled OR gate. So if we see any of the configuration like this bubble OR type, the configuration, we can replace that with the NAND operation. This is the fundamental principle for the NAND operation. Okay, so now we will see how the NAND gate behaves as the universal gate. To do so, to find out, now we will see by applying the De Morgan's theorem. We'll check how it behaves as a universal gate. So we know that for the two input, we are talking about the two input NAND gate. So this indicated by the bar. Okay, so if we know that for the NOR operation, the inputs are same. Okay, so if we can replace the another input with the previous one input, so it will be, see, if we replace this b with the a, so it will be a dot a whole bar, it will be a bar. Okay, so we just need to replace this. We have to just short these two inputs, and this will be the NAND, and this will create the bar. Okay, so this is the NOT gate. Okay, now next we will see the AND operation. So we know that if we put a NOT gate after the AND gate, it will create NAND gate. So again, if we put a NOT gate just after the NAND gate, ultimately it will become the AND operation. So what we have to do, this is the NAND operation, and this will go into the NOT gate, which we have implemented by shorting those two inputs. So this is the AND gate. Okay, this is the AND operation. Next is the OR operation. Next is the OR operation. How we can implement the OR operation. So what we have to do, we have keep only 2-3 theorems in mind, like De Morgan's theorem. And one more thing is that we know that from the basic Boolean theorem, that complement of the variable will be the variable itself. Okay, we know that the complement of the complement will be the variable itself. Okay, so if we see, A, we have to implement the OR operation, this. Okay, A plus B, not a bar. A plus B. We have to implement this. Now what? To do so, we have to apply this theorem. The complement of the complement will be the variable itself. Okay. So now what? This term and this term. This will be become what? This internal complemented thing will become A bar B bar the whole bar. Okay. So now what we have to do? We just need to implement A bar. We just need to implement B bar. Suppose this A bar is X and this B bar is Y. So it will become X dot Y this. So this is the NAND operation. So for this, what we have to do, we have to, this the final implementation will be like this. This is the function Y, or the AND operation is X and Y. Now, what are these X and Y? We have assumed that X is equal to A bar and Y is equal to B bar. So, how can we implement X is equal to A bar and Y is equal to B bar? Just short the inputs of the NAND gate. It will be this. Suppose this is A, which implement A bar, and this is B. This is B, which implement Y. So the implementation of the AND gate is like this. Okay, clear? Next, we will see. So you know the universal, how the different the basic gates, how we can implement the basic gates with the use of the universal gates NAND and NOR. Now, this is a simple Boolean expression. We have to implement this simple Boolean expression with the use of the NOR gate. Can you try this implementation? Can you try to do this? Can you try to implement it with the use of NOR gate? Try and tell me how many number of NOR gates are required for this. What we have to do? What we have to do is we just need to complement complement of the complement, and then the inside complement we need to solve that thing. We have to convert into the form of NOR or the NAND. Okay, so try to solve this according to the Boolean theorem, according to the with the use of the De Morgan's theorem, and the complement of the complement is the that variable itself. So try to do this. You have 1 minute and tell me how many number of NOR gates are required here. Okay, see. Now what we have to do, the fundamental principle is while designing, while implementing any of the Boolean expression with the use of NOR gate, what we have to do, we have to convert them into the NOR form. Okay, for this whole expression, we take the complement of the whole expression expression. Okay, we have to take the convert that into that form. So this and this. Okay, suppose this is we started from here only. So next what we have to do, this convert this in according to the De Morgan's theorem. Okay, so according to the De Morgan's theorem, suppose this is the one variable and this one is the another variable. Okay, so by considering them as a individual variables, what we get, here a plus b whole bar plus c plus d whole bar, and it is with the bar. Okay, so what we get here, this is one, this implement one NOR operation, one NOR operation, this will make one NOR operation, and if we replace this one with x, if we replace with y, so it will be in the form of x plus y whole bar. Okay, so now the simple, this will be converted. So this, the y will be like this, and the input are x and y. So, okay, so the y is this one y, output y. Okay, we are assuming this, suppose this is the small y. So now what we have to do, now we have to implement the x and y. So here x is equal to a plus b whole bar, and y is equal to c plus d whole bar. Hello? Yes, sir. Sir, my class is going on. Okay, so what we have to do here? See, this x is equal to a plus d whole bar, y is equal to c plus d whole bar. How can we implement? X will be implemented by just replacing this with the one NAND NOR. This will be a and d, and it will be x. Now we will replace this with c and d. It will be small y. So by connecting this, it will be converted into the NOR implementation. So how many number of NAND gates are required? How many number of NOR gates are required here? 3 number of NOR gates are required for the implementation of this a plus b multiplied by c plus d. Okay, so this is the simple implementation. Next, try to implement this AB plus CD whole bar with the NOR gate. AB plus CD whole bar. Can you try this? How many number of NOR gates we need here in this case? How many number of NOR gates are required? Can you try? Anyone? 3 number of. Okay. Okay. Let's try why. How many number of NOR gates are required here? We'll see. Okay. So we'll try to okay. First, we need to convert this into the NOR implementation. So to do so, what we have to do? We have to convert this AB plus CD. Okay. So AB, it will be converted into AB bar and CD whole bar. Okay. Now what we have to do? We have to make the complement of the complement. So complement of the complement. Okay. So if we solve this thing, if we solve this thing, okay, and taking this one variable, this one as the another variable. So what will happen here? It will be AB. See, we need to convert this into A bar plus B bar and C bar plus D bar. Okay. Then if we take the complement of this thing, complete 2 times complement. Okay. It will be A bar plus B bar plus C bar plus D bar, and this one with the bar and the whole bar. Okay. So if we observe this thing, we see this make the one term, this make another term. So consider this as the x, this as a y. So it will be converted into x plus is x plus y. Okay. So if we consider this, actually, and we need to consider this as the one thing, one term, and this one as the another term. So it will be converted into we need to convert this. Okay. So this whole thing will be like x and y. Okay. So it will be like x plus y whole bar. Okay. So this will make we can implement this x plus y bar with the use of one NOR gate. Okay. So this will be one NOR gate with x and y are inside here. This is the capital Y. Now what we have to do? We have to find out this. Here x is sorry a bar plus b bar whole bar and y is c bar plus d bar whole bar. Okay. So now what we have to do here, we need to convert this. Now we have to take these terms as the individual terms. So those individual terms will be taken as this we will implement this a bar using the NAND gate. Okay, using the NOR gate. So this will be A, this will be B, and so on. So it will implement A bar, B bar, this is C, it will create C bar, and the next one is the D bar. This will be shorted. So this will implement the D. Okay. So we have implemented these things. So after implementation, uh, A bar, B bar, the complement of this thing will be taken. Okay. So this will create the X. Okay. So this whole thing will create the X. So X will be what? X will be when A bar, B bar will be the input of this thing. So this, and Y will be implemented when the input of Y will be C dash and D dash. So C bar, D bar. So the here it will go inside. Here it will go inside. So how many number of NAND gates are required here? 7, not 3. Clear? Why not 3? Why 7? Because the terms A bar, B bar, C bar, D bar are coming here. So that's why here 7 number of NAND gates are required. Okay. So this is the NOR implementation. Can you try to implement the same expression with the use of NAND gate? This is a NOR implementation. Is it clear to everyone? Any doubt? How we are minimizing this thing? Any doubt about this? Roll number 1017. Any doubt? No. 1056. No doubt. Okay. Now it's clear to everyone. See. So next is we'll see. We try to find out how many number of NAND gates are required to implement this same type of expression. You try to implement this expression using the NAND gate. Now tell me how many number of NAND gates are required here. Anyone? 4. Okay. Anyone having any kind of doubt how to minimize this thing? No. So can I leave this example up to you? Is it okay? Okay. So next is the next expression is AC plus BC dash. Try to solve this expression, and then we will see the next topic. Try to implement this Boolean expression with the use of NAND and NOR. Okay. So what happens here? What we have to do again, we have to take the complement. After taking the complement, what we have to do, we need to we need to solve the one complemented the and one complemented terms like AC plus suppose BC dash. This is, so we are taking two complements, so one of the complement will be solved. So after solving this term, we get this A bar, B bars plus C and B bar, C bar actually. This is here should be C bar. Okay. So if we observe this thing, this is in the complement form. Okay. So, and if we observe this thing, this B bar, C bar will be replaced by B plus C, the whole bar. Okay. So this is the simple NOR implementation. This is simple NOR implementation. Now, if we consider this term, so here also we can convert this. So if we try to convert this in the NOR implementation, we see that here this is the A bar. So if we make this as the complement, if we take, so it will be B bar plus C. We take the complement of the complement, okay, and try to solve this thing. So and replace this. So this will be in the form of A bar dot and replace this as the Z. It will be in the form of A bar Z bar. Okay. So and if we try to solve this, so it will be what happened? How to convert this? It will be B bar C. So we just need to take the input of the gate will be what? Here one is the C and another will be B bar. So for this B bar we need to take use one more NOR gate. Okay, so what we have to do here, one NAND gate, another one NAND gate here, one more NAND gate here, one more NAND gate, and here the whole NAND gate. So how many number of NAND gates are required here? 1, 2, 3, 4 and 5 NAND gates are required here. Sorry, 5 NOR gates are required here. Okay, to here for the B dash we need one NOR gate, and for the whole this thing we need one NOR gate. For the whole this thing we need one NOR gate, 3 NOR gates. For this thing we need one NOR gate, 4, and the whole thing will require one more NOR gate. So 5 NOR gates are required here. Okay, we can implement the same expression with the use of NAND gate too. We just need to we need to solve this using the De Morgan's theorem. Okay. There's one more thing. In the gates, like we know the basic gates. Okay. How many number of basic gates are there? Three number of basic gates are okay in the if we talk about the digital electronics. Three basic gates are there, and or and not, and two are the universal gates. Okay. But in a there are two more gates which are very important while designing, while implementing any of the digital circuitry. For the different applications we require different logic gates. Okay. So those two gates are the exclusive or and the exclusive NOR gates. Okay. So there are two more gates are. Do you know about the exclusive OR and exclusive NOR gates? What are these gates, and what are the uses of those gates? Why we need two more gates? Because these two, if we talk about the universal gates, so if we have any of the function we implement by the universal gates, so for the different applications we need some for in the certain applications when we want to compare something, like if we say there are different some data is coming, and we want to check those two data are equal or not. For that purpose we require the exclusive or or exclusive NOR gates. Okay. So what is the difference between these two gates and the basic gates? So the exclusive OR gate is the gate which gives high value or true value when both the inputs are unequal. Okay. For the comparison purpose, in further classes we will see the how these exclusive OR and exclusive NOR gates are used for the different applications. Okay. We are working in the digital domain, so in the digital domain we implement some application, we design some applications, we implement using the gates, we fabricate those gates. So we try to designs for some certain application for the communication purpose, or for the transmission purpose, or for the logical manipulation purpose. Okay. So here exclusive OR gate are the gates which gives true or high value when both the it's both the inputs are different. Okay. So suppose A and B. Okay. So we have for the two inputs we have four combinations. So exclusive OR will be the value of the output will be what? Here this will be 0, this will be 1, and this will be 0, because the principle says it will be high when the different when their inputs are different. It will be low when the inputs are same. Okay. So those, if we try to solve this truth table, so the function will be a b bar plus b a bar. Okay. So here this is the exclusive OR gate, and we indicate this exclusive OR gate with this sign. Okay. And the simple symbol of this exclusive OR gate is this. Okay. So whenever we want to use the exclusive OR gate, we will use this symbol, and this is the expression, and the detailed expression is AB bar plus BA bar. What about the XNOR? The XNOR is just the complement of the XOR. Okay. So if we complement the XOR, we will get XNOR. If we complement the XNOR, we will get the XOR. Okay. So here it says XNOR says when the inputs are same, it will give high or true value. When the inputs are different, it will give low or false value. Okay, so if we try to solve this truth table, we'll get the expression like this: AB plus A bar B bar. Okay, AB plus A bar B bar, and its symbol is just we need to put one bubble with the exclusive or. Everyone, please put your scholar number in the chat box. This is inputs are A and B, and this will be Y. And with if we just put a bubble after in the exclusive OR gate, it will be converted into the exclusive NOR gate, and the expression we write like this. We indicate exclusive NOR with this. Okay, or if we apply a complement over exclusive OR gate, it will be converted into the exclusive NOR gate. So we have implemented the implemented the basic gates with the use of NAND and NOR gate. We just like that we can implement the exclusive OR gate and the exclusive NOR gate with the use of NOR gate and the NAND gate. Okay, so next is the from the first unit we have completed the up to the implementation of Boolean expression using universal gates. We have seen what are the different gates, all of the universal gates and exclusive OR and exclusive NOR gates. Okay, so next is how we can use this exclusive OR and exclusive NOR function in certain application. We'll see here. There's one more topic which remain from the first unit, and that is error detection and the error correction. So what is the error detection and the error correction? Here what happens whenever we design something that sometimes what happens, we have some information. If we are talk about the digital domain, that information will be in the form of the combination of some 0 and 1. So when the information is kept for the longer duration, so sometimes it happens that that information will get corrupted, or if the information is getting transmitted for the long and it covers the longer duration, what happens while it travel that medium, the medium can be anything, whether it is a wire or the air is the medium. Okay, so while traveling through that particular medium, sometimes the glitches or the noise or anything there's a possibility that any kind of thing can change the bit stream of the valid information. So the transmitter or the sender is sending some kind of information, but while it travels through the medium, what happens sometime the zero, or because the information is in the form of a 0 and 1 combination of 0 and 1, so it happens that 0 will get converted into 1 or 1 will get converted into the 0 because of the noises associated with the mediums or the circuitry. If we don't design the circuitry efficiently, so what happens that errors or the glitches or the noise will corrupt the valid information. So if the sender has sent the information, it get corrupted through the device or through the medium, so the receiver will get the wrong information. So we don't want that thing to happen. What we want the reliability, that whatever transmitter is sending, that information should be received by the receiver correctly. To that, for that thing, what we do, we require the error detection and the correction codes. So in the error detection and the correction code, what happens, there's some in for the detection purpose, we add some extra bits for the reliability purpose. So those extra bits with the valid data is known as the parity bits. Those extra bits are called as the parity bit, whether it is the even parity or the odd parity. So after adding the extra bits, and when the receiver receive that information with the added number of bits, it checks whether the whatever parity with the parity is added there, if it is in that form or not. So that addition of the parity bit will ensure that we can detect that kind of error. But the addition of the parity bit does not guarantee, it does not include the correction. We just receiver just get the information that there is something happened with the valid code. So we'll consider this thing in the next lecture, and we will finish the whole first unit after doing this studying this error detection and the correction. Okay, so any doubt till now? No. Okay, so in the next lecture, we will see how the error detection and correction codes are very usable for the reliable transmission of the information.